Now we will try to understand two fundamental theorems used in probability through some simple examples. The first theorem is stated as follows. Suppose we have two events A and B. Then we can assign the probability for both of these events. So let P of A be the probability that event A happens. So these are just the notations. P of B is the probability that event B happens. But in certain cases, these two events A and B can be linked to each other. So we can define another term like P of B with some subscript A. So let us call it as PAB. PAB. So this notation implies that event B happens if we know that event A has already happened. So this puts a restriction on only those possibilities of event B when event A has already happened. Now we can define another notation as P of A into B or P of AB. So this means that probability that events A and B both happen. And we can also define another probability P of A or B. Actually this is called as P of A and B. So there is a dot symbol here. Of course that dot can also not be written. It is equally okay. So P of A or B. So plus sign indicates logical OR operation. In that sense it is P of A or B. Says that either event A or event B or both can happen. So these are the typical notations which we are going to use while discussing these two theorems. So let us shift our discussion again to the first theorem. If we assume two such events A and B, then the first theorem states that P of AB is equal to P of A multiplied by P of B such that A has happened. So this is an expression for the first theorem. Now suppose that event B and A are independent. So they have nothing to do with each other. In that case, P of AB is not affected at all by the happening of event A. So in such case, when A and B are independent, P of B with subscript A is same as just P of B. In that case, this equation gets simplified to P of AB equal to P of A into P of B. So this is the modified version of the first theorem in the case when events A and B are independent. So this is called as first theorem of probability. Let us move to the second theorem. For the same two events A and B, P of A or B would be given as P of A plus P of B minus P of AB. So P of A counts the probability of happening of event A. P of B counts the probability of happening of event B. Since A or B both are allowed to happen, we are going to add the two probabilities. But we should note that we have to subtract the intersection part of A and B. So this is the effectively intersection part of A and B. So while counting P of A and counting P of B, we have already counted this intersection part. So in order to avoid this repetition of counting the probability, we need to subtract this part, which is the probability of events A and B both happening together. So this second law of probability gives the probability of happening an event A, either A or B or both. Now in this case as well, there is a special case. If events A and B are mutually exclusive, that is, they do not have anything in common. So using a Venn diagram, we can show it like this. A and B are completely or we can say mutually exclusive. So A intersection B part does not exist. So nothing is common between them. In that case, P of AB, the probability of happening of both the events is going to be simply 0. So the second theorem also gets modified when A and B are mutually exclusive as P of A or B is equal to P of A plus P of B. This is the special case of this second theorem. So since we already have with us both the equations representing the two theorems, let us take an example in order to understand these theorems better. Suppose there are two students. So this is an example which explains these two theorems. Suppose there are two students which are trying to solve a problem. So both of them have a different capability. So we can assign a probability that every student is capable of solving the problem. Suppose the probability that first student solves the problem is 1 by 2, and probability that second student solves the problem is say 3 by 4. So first student has a 50% chance, that is 1 by 2, of solving the problem, whereas the next or second student has a 75% chance that he or she solves the problem. Now a question can be asked in the following way. So what is the probability that at least one of them solves it? At least one of them solves it. So we need to find out an answer to this question. What is the probability that at least one of them solves it? So let us define two events, event A and B, as plain. So event A is the probability that first student solves. So P of A would be 1 by 2, and this is the probability that second student solves. So P of B will be 3 by 4. Now let us try to find out P of AB. We must note that both these students are trying to solve the problem independently. So they are not going to consult with each other. So that is the main important assumption. In that sense, both of these events A and B are independent. Because it doesn't matter whether this first student solves the problem or not. If the student B solves it, then he is going to solve it. If he is not able to solve it, then the problem will not be solved. So it doesn't matter whether the event A happens or not, it does not have any effect on the happening of event B. So both of these events are independent. So in that case, P of AB by first theorem will be equal to P of A into P of B. That is 1 by 2 into 3 by 4, which is just 3 by 8. So this is an expression for P of AB. But we are asked to find out this particular probability that at least one of them solve it. So what does that mean? At least one of them solves. So at least one of them solves. That means that either A solves it, or B solves it, or both of them solve it. So this is nothing but P of A plus B as per our earlier discussion. And we know that P of A plus B is equal to P of A plus P of B minus P of AB. So let us just substitute the values available. P of A is just 1 by 2 plus 3 by 4 minus, we have calculated the value for P of AB as 3 by 8. So this can be further simplified as this is 6 by 8, this is 4 by 8, right? So this is just equal to 7 by 8. 7 by 8. So this is approximately 0.87, right? Or 87%. So we can see the effect of teamwork here. When they were trying to solve independently, the first student solves with a 50% probability, that is 4 by 8. The other student solves with a 75% probability, that is 6 by 8. But if they are made to solve it simultaneously, independently, the probability that it is solved is 7 by 8. So the probability is obviously going to increase if multiple persons are allowed to solve the same problem. So this is how we have used both of the probability theorems in this case, namely the first theorem and the second theorem. Let us try to find out or study another such example which is a slightly different case. Suppose, so this is the second example. Suppose there is a box which is closed and there are 5 black balls and 10 white balls available inside this box. So we are going to perform an act where we are going to draw 2 balls one after another. Draw 2 balls. So let us draw first ball, and when the first ball is removed, so in the initial stage there are total 5 plus 10 equal to 15 balls present. So initially there are 15 balls present. We are going to draw first ball, and then without keeping it again inside the box or replacing it, we are going to draw a second ball. So when we are going to draw second ball, we are left with only 14 balls inside the box instead of 15, since first ball has already been removed. While doing so, suppose we are asked to find out the probability that first ball is white and second ball is black. What is the probability that this is going to happen, that first ball is white and second ball is black? So let us define the two events again. Event A says that first ball is white. Of the 15 balls available, and event B says that second ball is black of the available 14 balls, since the first ball has already been removed from the box. So clearly P of A is going to be the number of sample space in the denominator and number of the white balls present in the box. So that is simply, since there are 5 or 10 white balls, so it is 10 divided by 15. So this is the probability of getting a white ball out of the 15 total balls present inside the box. Now P of B with subscript A. Why are we writing so? Because now in this case event B takes place after the event A has already happened. So they are no longer mutually, they are no longer independent. So P of B in this case is now going to be n of B divided by n of S. Now note that n of S has already been reduced. It is now 14 since one ball is less now in this box. And since there are 5 black balls left, n of B will be 5. So the total ratio is going to be 5 by 14. Now what would be P of AB? Because we are here asked to find out the probability that first ball is white and second ball is black. So P of AB says the probability or implies the probability of happening of events AB both collectively. So that is just P of A into P of B with subscript A, which is 10 by 15 into 5 by 14, which is just 10 by 42. So this is the answer to the original question. Let us just have a flavor of another example which we may be looking at in the next video. Suppose we are going to toss a coin 3 times. Toss a coin 3 times. And what is the probability? So this is an acronym used for a longer version called what is the probability that. So what is the probability that all 3 are heads? So we already know the answer to this question, because when a coin is tossed 3 times, the sample space starts from HHH, then HHT, HTH, THH, TTH, THT, HTT and TTT. So there are total 8 available outcomes, and all 3 are heads correspond to only one of the outcomes. So that is just the ratio 1 by 8, which is the answer. But let us try to solve the same problem using the theorems. So we can define 3 events. Event A, coin is tossed first time. Event B, coin is tossed second time. And event C, coin is tossed third time. When a given coin is tossed, probability that a head will occur is just 1 by 2, because there are 2 sides to a coin, head and tail, with equal probability of 50%. Now the same coin if tossed next time, that is event B, again the probability that we will get a head is just 1 by 2. Similar is the case with event C when the coin is tossed third time. So again the probability of getting an head is 1 by 2. So we need to calculate the probability that all 3 are heads. So that is nothing but P of ABC. And we should note here that all these 3 events A, B and C are obviously independent. So P of ABC will be simply P of A into P of B into P of C according to the first theorem, which is 1 by 2 into 1 by 2 into 1 by 2, which is equal to 1 by 8, which is the answer which we have already got. So this was a brief discussion regarding the two fundamental theorems of probability. Thank you.